Okay, well, I think we have a pretty good number. Why can't I back up? There we go. Have half the people who registered have already joined. So I'd like to welcome you all to the first in our tutorial series. Could everybody please mute? And today we're going to start out by helping you deal with Musica version 0 output and how to plot it and use it. So to start, I just want to remind everybody that the presentation is being recorded, and we hope that we'll all have respectful dialogue with each other throughout this session. So just to summarize what we have in mind for the whole tutorial series, in general, we wanted to give people an idea of introduce you to the various components of Musica. The variable resolution global modeling capability that we're calling Musica version 0, also to box modeling, which is Music Box, and then also model evaluation, comparing the 3D model to observations with our melodies package. So today we're going to use Musica version 0 output, and we thought this was a good start for those of you who are interested in running Musica version 0. You need to know how to deal with the output once you've learned how to run it. And maybe some of you would just like to use some of the simulations that we're providing. We have a community simulation I'll tell you about. So that this should be able to get you started with that. And then we'll show you how to create your own variable resolution grid, because I know many of you are interested in doing that, and how to run Music Box and melodies. And we are welcome to your input on what would be most useful for this tutorial series. So I just wanted to summarize that you're a very diverse group, and maybe through this tutorial series, we can help develop collaborations on these many different topics that you're interested in, and many different regions of the world that you want to simulate. So many of you have already run CESM, but a lot of you have not, and we'll try to help you out, get started with that. And it looks like many of you are far more expert in Python than I am. So hopefully you'll still find this session useful and helpful. And you have a wide range of experiences, from grad students to postdocs to professors. So we're going to do our best to make this useful for all of you, and apologize if it's too simple for some of you. So for today, I'm just going to give you a brief overview of Musica, tell you a little bit about what unstructured grids look like, and then describe briefly this simulation that we've put on the web for people to use, what the format is, and what are in the output files. And then I'll hand it over to Dusong, who will show you walk through the tutorials, and then we'll have time for walk through the Jupyter notebooks for plotting the output. And then we'll have time for people to try things on their own, and we'll be around to answer questions. And so really the goal of today is just to introduce Musica, introduce the output so that you know what it looks like and how you might use it, and use the Python notebooks. So Musica, probably many of you are somewhat aware of what Musica is, but our goal for the whole project is to build an infrastructure that will really facilitate more flexible development and use of different components in a global Earth system model. So having different modules for a chemical solver and aerosol schemes that connect through a standardized interface to an atmosphere model, and then also be part of an Earth system model and connect to a land, ocean, sea ice model, etc. And it's not just for air quality, but we also, it will be useful for whole atmosphere studies. So there's a web page, the Musica webpage, which I'm sure you found because you got to the tutorial. And there's a paper published in BAMS last year that really describes the vision for Musica. So there are really two components to the Musica effort so far. The first is developing this independent chemistry module and including it in a box model called Music Box, so that we really have sort of a database of all the stuff that goes into a chemical reaction, and then a tool that writes the Fortran code of the chemical solver that can then be plugged into a model. And so Music Box is this solver in a box model and has a very nice flexible browser interface for changing inputs, the chemistry scheme, varying the initial conditions and that sort of thing, making plots and comparing different mechanisms. So if you're interested in that, feel free to go to the GitHub site to get Music Box. So the other aspect is having a variable resolution within a global model. And so currently we have the spectral element dynamical core in CAM-CHEM, in CESM, which allows for a variable resolution grid like this on the left. And we're also working on adding MPaths to CESM, the model for prediction across scales, which uses this hexagonal mesh, which also allows for variable resolution and can even go down to non-hydrostatic scales, such as 3 kilometers or so. So that's a work in progress, and it'll be available at some point soon. So Musica version 0, what we're calling that is really CAM-CHEM with a spectral element and regional refinement. And using this CONUS grid, there's a component set, so a default configuration in CESM that allows you to run this configuration fairly easily. And so we're really excited about the capabilities of this, that with finer resolution, we can more accurately represent the emissions in chemistry in the finer grid. But it's embedded in the global model, so feedbacks are directly included. And most of the grid points are in this refined region. So there's really very little cost for simulating the whole globe over running the CONUS region at 14 kilometers. So we already have a few results. Becky Schwantes has just submitted a paper to James describing this case, and Forrest Lacey is working on another paper. Really, they've done the first really hard work of evaluating this CONUS grid with chemistry and also comparing two different chemical complexities with this grid. And so you can see that with 14 kilometers, we're really more surface ozone is more detailed over the eastern US, and it also changes how ozone is transported out over the Atlantic. And another case, Wenfu Tang has been looking at FireX using this CONUS grid, the field campaign in 2019, looking at wildfires in the Western US. And this plot really shows the specific grids of this 14 kilometer grid with the DC-8 aircraft flight tracks, showing that this is a good resolution for making these direct comparisons to observations. And Dusong has built a grid over Korea with 7 kilometers over Korea, the Korean Peninsula, and slightly coarser grids gradually across East Asia to look at air quality over Korea and the region. And one final new grid that we've been working on is this large grid over East Asia. It has about 25 or 30 kilometer resolution over this large region to look at the Asian monsoon, and in preparation of the ACLIP campaign, which is expected to take place next summer, to look at the outflow of the Asian monsoon flow over in the upper troposphere and out over the Pacific. So we can see that with the finer resolution, there's far more CO transported to the upper troposphere, the 100 hectopascals, and then getting transported and shed over the Western Pacific. So finally, the Melodies project we're currently developing, and the plan is to make it much easier to compare observations and models than is generally possible, so that we'll have a Python-based tool that reads in different types of data sets and different types of model output, and then matches them and performs various analyses and making plots. And so we're currently working on this, and it's being built on Monet. You can read about Monet, and we hope to have the Melodies Monet GitHub site available for people to look at and help us develop in the next few weeks. So I just wanted to summarize that the Musica goals are really to encourage collaboration on these variable resolution and modular chemistry ideas. And we hope that you'll be interested in working with us on further developing it, and also using the tools that we already have. And so we hope to really be able to improve research in a variety of aspects, air quality, all aspects of chemistry and aerosol research, and to connect to policy relevant activities. So there were various ways to become involved. We have a number of working groups. If you're interested in developing particular aspects of the model, you can join any of these working groups. There are email lists to get updates for the newsletter. Get a newsletter we've just started producing every month or two, and other updates. And we'll show you how to access the simulations and contribute to our other codes. So now to get down to the specifics of Musica and the grid. So I'm not going to go into great detail of what the spectral element grid is, but if you're interested in all the mathematics of it, I highly recommend you read Peter Lauritzon's paper that describes the spectral element in CESM2 and shows how the grids are treated. He also has information in his CESM2 tutorial lectures, and he also gave a lecture at workshop we held several years ago on the fundamentals of atmospheric chemistry and aerosol modeling, which you might find useful. I should have said that I have posted already a PDF of this presentation on the tutorial webpage, so you can download it and access all these links. So spectral element has really been in CESM for quite some time, and one of its benefits is that it really is quite scalable. It can be used for GPU acceleration, which is something we're really just starting to work on, and has the capability for mesh refinement. So that's why we started using this for Musica. And so the grid is unstructured. It's maybe many of you are unfamiliar with. It's not a regular lat long grid. So you get an output that's just an array of points that can be anywhere on the globe. But the model output gives you the lat and long of each point as separate arrays, but the edges and vertices of this grid are not in that, in the standard model output file. So we have a script file for each grid, and the Python tutorials will point you to the appropriate grid to the appropriate file so that you can actually plot each point and its appropriate area in these new notebooks. So it may take a little while for the Jupyter Hub notebooks to start. So for those of you who have accounts on Casper and Cheyenne and want to play with the Jupyter Hub notebooks later on, I encourage you to start up the, I don't know if this won't show, the Jupyter Hub. So I just stop sharing and I'll share this other one. And so you go to this web page. Hopefully people will have that. Try to put it in the chat. And you select production, and then you enter your username and password, and it will ask you for your Duo authentication. And then you will get this web page that says, you click the blue Start My Server button. And that, and then you have to fill in first, select the Casper PBS batch. So you can just use the login nodes, but those don't allow you to select more memory, and they sometimes are a little bit flaky. So, and then Casper and Cheyenne in general look at the same directory structure, so the same GLADE disks, but we also have something called campaign storage, which is only accessible from Casper. And that's where we have these big, the long run of the CONUS grid simulation that we want to use for plotting. So we've asked you to pick Casper batch node, and you'll just need to enter a project number and probably need to increase the memory. Maybe 5 gigabytes will be good for this. And you can increase the wall time. If you're going to do something for all day, you can put in 8 hours of wall time, so it doesn't kick you out. But that also ties up resources for other people. You should pick the smallest wall time possible. Yeah, sorry, I'm not sure I can help with all the password issues at the moment. I also wanted to let anyone ask questions about anything I've said already. So welcome to take any questions about Musica in general. And so hopefully that's then you get to this page of your server starting up, and this is where you might have to wait. So I will go back to my other presentation. And so this, we realized a lot of people may not have the resources to run the CONUS grid simulation, and there are a lot of field campaigns that maybe people would like to use the model results to analyze with them, or any other sort of use. So we've made this simulation available, and it's just been posted on the Dash repository. So it's this output is the CAM-CHEM with spectral element simulation with the CONUS grid, uses the standard Mozart TS1 chemistry that's in the standard CAM-CHEM simulations. And we've nudged to the MERA-2 reanalyses. So far, we've only run 2012 and 2013. And we've used these emissions. So the latest CAMs, anthropogenic emissions, use QFED emissions, where we've applied FIN emission factors to the QFED CO2 emissions. Biogenic emissions are calculated online in the model, in the community land model. And we also have a module called OASIS that calculates DMS emissions for the ocean. And we've added a number of carbon monoxide tags so that you could use those to analyze source contributions from various regions or from biomass burning from the whole globe. So the output is now available on the Dash repository. And the files that are available there are what we call the time series files. There's a separate file for each variable, each compound, each chemical compound, and there are a number of other physical parameters and diagnostics that are available. And so there's a file per year for the monthly averages. There's one version that's interpolated to the original, to our standard 1 degree regular grid. And there's another version that's just, it's a smaller set of variables, but it's on the native resolution. And then there's some daily averages that are grouped in monthly files, and there'll be, we have some hourly output that will also be available soon. And we have run another simulation that's at a uniform NE30, the spectral element 1 degree resolution for 10 years. And that's also available. And we'll be posting that on the Dash repository also. And this will also be useful for providing initial conditions if you want to run your own simulations, either with the CONUS grid or some other grid that can be regridded. So this is what the Dash repository looks like, web page. It's a little description of the case. It has a DOI, so if you use it, you can use this output, you can reference it. And there are various ways to get the files. You can just look at a list of the individual files, get a zip file containing all the files, which I do not recommend because that will be just huge. And ways that you can get shell scripts for different, for the sets of files. So if you go to the download files page, click on the individual files, it will show you a great many pages of files, but you can subset them by typing into the search box some fraction of the name, like H0.03 will give you the monthly average ozone files. And then you can download those easily.
You're not gonna go?
No, it's in my coast there.
And so once you have the files, the standard regular grid files have dimensions of lat, long, time, and level. But the spectral element files just have a number of columns, time, and level, and then additional variables of lat and long that are dimensions, have the dimension of each of these points that will give you the points for the whole globe. And then so variables like ozone are a function of time, level, and NCOL, and as opposed to time, level, lat, and long. But they don't contain all the information, so that's why we need a script file. And then also there's, just want to say briefly about vertical information. So CESM output is indexed from the top of the atmosphere to the surface. So index 0 or 1, depending on your language, will give you, you know, the middle of the stratosphere, upper stratosphere. And if you want the surface, you want level 31 or 2, or in Python, just use -1 to get the bottom, the last element. There's a variable lev in the files, but that's the global mean pressure for each model layer. So it's good for a quick look and a general idea of what the vertical resolution is, but you'll probably want to use something like P-mid to give you the pressure of each grid box if you're wanting to look at vertical structure. Thanks. There's also a variable called Z3, which is the geopotential height, and you might want the surface pressure. And P del dry is the layer thickness, the pressure, delta pressure thickness of each layer, which is helpful for integrating columns, that sort of thing. So we have a lot of variables, and I'm not going to go into the chemistry scheme at all. You can look at my paper in James. It has in the supplement the list of all the chemical compounds and the reactions, if you're interested. There are a lot of meteorological outputs that are saved in these files, and diagnostics like the boundary layer height. There are also a lot of chemistry diagnostics like the emissions, just the totals, all sectors of the surface emissions, or just the biogenic emissions, or integrated columns of the surface of vertically distributed emissions, and also specific variables for lightning, and things like the deposition velocity, deposition flux for wet and dry deposition. And these two web pages can provide you with more information about output available in CESM. So when you run the model, you get a variety of different output files directly that are in, we call history files. And so there are many variables for chunks of time. So we have H0 files, which are monthly means, H1, which have been interpolated to the 1 degree grid. H1 files are on the native grid. Now, so this is specifically for this CONUS simulation. If you're running a simulation or somebody else has run a simulation, that you can assign these files to be anything you want. H2 files are daily averages. H3 have 6-hour output, but these have been interpolated to the 1 degree grid, and we save these particularly to be used for boundary conditions for regional modeling, if anybody's interested in that. And then we have a few species on 1 hour at 1 hour output on the native grid. And most of these are just surface values, not the whole 3D. And then we often process these files to make a time series file. And so they have the same labels, H0, H1, H2. And this is what's on the Dash repository for you can download. I'm not gonna go through all of this again. I separated this out sort of as a different way, but you can look at that online if you want more information about all the files. So next, we're going to move on to demonstrating how to actually plot things. And I'll pass it over to Song in a second, but this is the web page with the notebooks, which hopefully you've all found. And we also have a web page of other CamCam plotting tools from Python. And we hope that if you're developing new tools, have figured out new ways to do things, that we'd welcome your contributions to this. And hopefully you also find these useful in your work. So I'll pass this over to Dusong now.
Okay, thanks. Yeah, hi everyone. My name is Dusong. I'm a postdoc at NCAR-ICOM. So I'd like to show the Python examples for unstructured grid output simulated by Musica version 0. So just a little bit of logistics. I'll first share my JupyterHub screen, and I'll demonstrate some examples shown here. So examples include how to read Musica version 0 output files, view file structure, and basic array manipulation, and various two-dimensional map applications, such as global or regional plots, adding a custom color, overlaying observations on the plot, make plot on a log scale, multi-panel, or adding grid lines, etc. So we'll look over each item step by step. And we'll also go over some analysis tools like calculation of emissions and vertical profiles, cross-section, and time series analysis at a specific location. And lastly, we'll also learn how to regrade unstructured grid data to structured grid data and save the structured grid data as a new Xcdf file for further analysis. So basically, that's what we are going to learn. And then after this demonstration, as Luisa said, we'll have some time to let you try your examples on your own. And then we'll open some breakout rooms to answer your questions if you have. Basically, you will ask questions in this main room, and then some of us who have some experience with Musica version 0 output will help you. So we will go together into a breakout room to figure out the problem you have. So without further ado, let me share my screen, my JupyterHub. Okay, I think you can see my screen. So yeah, thanks.
Yeah.
So it looks like some of you have some problem logging JupyterHub. I'm sorry for that. But as Luisa said, we have this GitHub page, so you can just download example files on your personal laptop, and you can also download the community run files, and you can try examples on your laptop as well. So if you have your JupyterHub ready, then you can also follow my demonstration on your JupyterHub as well. So let me explain briefly about the 4 different examples. And first one is map examples here. So for Python, for those of you who are not familiar with Python, you have to first import libraries to be used in this notebook file. So libraries include like some for calculation and some for plotting and for the analysis. And then first you have to read files. So in this example, we read two files, one from Conos ROM that is 8 times magnification over Conos, and 1 degree global run file. So we will use these two files, but just in case you want to play with some community run files that Luisa showed earlier, you can just uncomment these lines and play with different files, and you can plot different outputs. But for this session, we'll just use these two files. So once you read the Xcdf data generated by Musica version 0, then you will have these variables. And reading Xcdf in Python is actually easy. So you can just call this open underscore dataset function to load Xcdf file and pass it to the variable. Here we have ds underscore Conos variable here. And you may want to know which data is included in this ds Conos variable. And then you can just simply type your variable name. And if you press the shift and enter, then it will run the Python shell like this. And then it will show some information of the data set, like the dimensions and coordinates. And you can expand the data. So you can see the data variable names. And also, if you are curious about, for example, the unit of carbon monoxide in this output, then you can click the paste button here. Then you can see the units and other information saved in the Xcdf file. Then I included a few examples for some basic Python calculation. So in the interest of time, I only included a few examples here. But for some of you are not familiar with Python, and if you want to learn Python, I would recommend you see this web page to learn Python. But in this example, I only listed very few examples here. So first, you can check date like this. So you can check date and units of variables. So in this example, for ozone and surface flux or carbon monoxide, and shape of array. And you can also calculate minimum and maximum of variables globally as well as at the surface. As Luisa said, -1 means the surface layer in this Musica version 0 output. And you can also do some arithmetic operation if you want, like this here. So plus or minus, or multiplication or division, whatever you want. You can do some calculations like this. And then let's move on to the real plotting map examples. And also Luisa said earlier that we need the script file that has grid information that's needed to plot values on the map. Especially for this example, we need grid center and corners to plot the variables on the map. So we need this grid information file. So the first example is global map. You can plot the global map by simply calling this function named plot underscore 2D. So it basically calls some plotting function, and it can draw a map like this. So you can just put your variables here. I just multiplied by 10 to the 9 to make the unit to ppbv. And you can also specify some maximum value of this caliber, and you can add the unit like here using these keywords. And you have to pass the script file to let this function know about grid information. And And then you can get this kind of basic plot. You may want to plot some regional map like this. So again, the procedure is very similar, but now you have 3 more keywords in this example. These two to refine your region. So you have to specify the longitude and latitude ranges to make the regional plot. And here, another keyword state is if you want to add the state lines like this, then you can set this keyword true. So if we set this keyword first, then it will just show some country lines and coastal lines, but no state lines like this. Okay, the next example is if you want to change caliber with some custom labels, then you can add these 2 more keywords to make your own caliber. So for example, here I set the galactic location and the labels, and then you will get the plot with the custom labels like A, B, C, and D here. And for a more advanced example, you can also add a location point on the map. But here, the example is a little bit different. You may notice that here, so in the above example, you call the plot2D function, but you don't pass the output of the plot2D to another variable. But here in this example, you pass the output of plot2D function to this p variable. We call it instance in Python, and it has a lot of information to play with. And by making this variable p, you can add more information on the plot like this. So you can call the simple plot function to add some circle marker on the map in this line. And you can also add the text here using this text function. And here is another example we included. If you want to include some observational points like this in the circle, then you can follow this way. So first part is the same as above, but we made the plot somewhat larger. So actually you can specify the figure size like this. The default figure size of plot2D function here is, I think, 8,5 in this case. And you can make it larger using this function. And then you have to add some subplot. Here is just 1x1 panel, but I will explain the meaning of each number later on. Then you have to get some observational data information. So in this example, we provided some annual mean ozone by comma split format. And you have to know the latitude and longitude and values of observations. And then you have to do something to make the observation circle color scale match with this map. So here divide by 80 means because we have the maximum value of 80 here. And then you can add each circle by using this for loop. And by calling each circle with some different values, you can get these kinds of maps, so overlaying observational points on the map with background model concentration. Another example is a log scale plot. You can also plot it on log scale, especially when you want to plot the emission flux, because emission flux varies several orders or magnitude globally. So you may want to plot it on a log scale. Then it's simple. So you can just turn on the keyword log scale, set true. then it will show some log scale plot. One caveat here is you also have to specify the minimum value of the plot, which was not in this above example. We only specify the maximum value here. But as you know, because we can't have the log 0, so you have to specify the minimum value like this. And then you can get some log scale plot shown here. And then you also may want to get some multi-panel plots like this below. Then you can plot the result like this. So first, you also have to make a new figure. And then the first half is for the left panel, and the second half is for the right panel. Here, let me explain the meaning of these numbers. So the first one is row, and second is column, and third one is row order of each plot. So row, column, and order, and I think this starts from the top left corner of the multi-panel. And in this example, we have one row and two columns. So you can add some multi-plus in this way. If you want to 4 plus 2 by 2, 4 plus, you can just change this number 1 to 2. Then you will have 2 by 2 plots. And another thing you may notice is I added also two another keywords. So first one is title, and second is the column wrap keywords. So I changed the column wrap here using these keywords. So if you want to change the column wrap, then please go to this website. Then it will show a number of column wraps shown here. So you can select whatever you want from this column wrap table. So let's move on to next example. So sometimes you want to have just one big color bar for the multi-panel plus. And this example is making just one big color bar. So for the first half of this example is the same as above, but we now suppress the color bar because we don't want to generate color bar from plot 2D for each panel. So we just suppress the color bar here. And then we manually add a big color bar using this color bar function. But you have to first specify the color bar axis. I think the first one is left and bottom, width, and height. So you can set the color bar position in this way. And then call the color function to make color bar. Here you can add several keywords like this. So for example, extend both means you have some triangle here. So over 300, you will have the same color as exact 300 value. And also if you have some values lower than 0, then you will have the same color that used for 0. And you can also change orientation like vertical or horizontal. And again, you can add a text to the plot. So you can add a unit in this way. And you can add a big title here using this text function. And this is the last example of this file. So you may want to save the result as some PNG or JPG or something else. So in this way, you can save the result as a PNG file. So this is very simple. You just add one more function line to save the result as PNG file. And another thing you can notice is here we added the grid lines by using grid line keywords. So set the grid line keyword to true. and specify the line width of grid line, then you will get this plot. And sometimes you may be curious about how to use this function and how many keywords you can use in this function. Then you can just put a question mark after any function. So in this example, you can put the question mark after this save big function. And then you can get some detailed usage. So for example, you can get some calling structure, and you can specify DPI or quality of the class. And also you can change the format like PNG, PDF, SVG, etc. So if you have any questions about this function and curious about the keywords that you can use using this function, then you can just put a question mark for any function you want in this example. Okay, then is there any quick question for this example? We'll have some time to get your questions, but if you have any quick question, then we can address now. If not, we can move on to the next example file for analysis. In this example, we'll see how to calculate some global emission total from the unstructured grid, and also zonal mean and vertical profile. So we'll address these analysis. So again, you have to import library for some calculations and plotting, and you have to read files. But in this example, we read 12 files at once. So you first construct 12 files for the year of 2013. And then you can read the multiple files at once by using this function called open mf dataset. So in the previous example, we used open underscore dataset, but now we use the open underscore mf dataset. I believe this stands for multi files. Then you can get 12 files at once. And again, assign the Xcdf file to this variable. And again, you need to have script file for the analysis. Then here is the part for calculating emission total. So the process is simple because at NCAR, we have some predefined function to calculate emissions. So you can simply call this function to calculate emissions. The first one is for global emission, and the second one is for regional emissions with this keyword. So this is for the surface flux or the carbon monoxide in the model. And you also have to specify the molecular weight to calculate the global total emissions. So we have these two examples, like for global emission and regional emissions. So this is simple with this predefined function named calc_mst. And then let's do a quick check of this variable. So you can just draw a simple line plot shown here. So you can first also set the figure size, and then you can the simple line plot using the output from this calc_mst function. Actually, this part is just to polish the plot. So if you uncomment this part, you will also see some plots, but it is just to polish the plot. Basically, this one line do the plotting, and others to make some plots better. Like you can increase the font size, and you can add labels on X and Y axis, and you can add some title. It looks like we have some questions on the chat.
No, nothing specific.
Oh yeah.
That's okay.
Yeah, so we are recording this, and it will be available later. And let's move on to the vertical profile. So now we'll calculate some vertical profile for ozone over Colorado region in this example. First, we included just one line. One usage of this data set is you can actually get a slice from the data set you loaded. So you can remember we loaded 12 files in the above example. So now we just want to just generate data. Then you can specify the time dimension and time equal to 0. Then you can get just the first file in this way. And let's play with the new data set. Here we define the Colorado region, and then we got the longitude and latitude values from the model output. And you can find the indices for Colorado using this where function available in Python NumPy library. And then we can calculate some mean ozone profile over Colorado region. Here we calculated some ozone mean profile, and O3S is also ozone, but from the stratosphere. So you can look at some stratospheric influence on tropospheric ozone from the Musica run. And also we can calculate some geopotential height for this vertical plot below. So in this way, we can calculate some vertical profiles and then plot these. So again, just a simple line plot. So they are almost the same as the above example line plot, but now we have two lines in this example, and we added a legend to show the information of each line. So you can just add this function line to add a legend. And to use this legend, you have to specify the label of this each plot. So in the above example, you don't have the label keyword here in this plotting function. But here, if you specify the label, then you can add a legend here. And next example is about how to calculate cross-section. So because it's very difficult to calculate cross-section from the unstructured grid data set, we have to regrid data to a traditional latitude, longitude grid to calculate zonal or meridional cross-section. In this example, we regrid our corners run to global 1x1 grid. So we first specify the longitude and latitudes, and then construct some random grid using this mesh grid function. And using this grid data function, we can regrid this unstructured data to structured data set. And then we can easily calculate the zonal or meridional cross-section. Here we calculated some zonal mean here, but if you change this value 1, this is for dimension. So if you this dimension variable 1 to 0, then you will get meridional cross-section instead of zonal mean cross-section in this example. So with these examples, again, just for a quick check, we plotted the results here. So you can just simply plot the zonal mean cross section using this line plot function. And we also included another way to calculate cross section because this grid data method could be problematic, especially because it uses some linear interpolation. So you may want to some conservative regrading. So we also have some predefined function to calculate zonal mean or meridional cross section that considers the area of each grid. So in this example, you first have to get the area information, and then you can just calculate zonal mean cross section from this function. And again, for the quick check, can get the zonal mean cross section from this method. And if you compare this plot to this one, then you will notice some differences, but general patterns are similar. And if you want to do some more advanced method to regrid unstructured grid data set to structured grid, then you can use ESMPY library, which is a great library that can do different regrading methods like linear and first order conservative, second order conservative, neo-least method, etc. So for advanced regrading method, please check out this website to find out the different regrading method for your analysis. Okay. Do you have any questions for this example? Well, it looks like Luisa is answering all the questions. So let me move on to time series analysis. In this example, we'll see how to pick up a specific location and plot time series. So again, we have to load library first, and then you have to read files. In this example, we use different files from the community runs, H4 files. The detailed information is available in Luisa's slides. Here we read 31 files for the August 2013. And then we also again have to get the information for script file. And here in this cell, we find the index of each city. So here we picked up 3 cities, so Denver, LA, and Centerville. And we can get some city location index from this get site index function. So you can put the longitude and latitude of city you want, and then it will return the index that city is located in Musica version 0 grid. With this index, then you can extract the time series of ozone or whatever in a city. So here in this example, we extract ozone at the surface using the index calculated above. So we have 3 time series from 3 cities using this for loop in this cell. And we can draw some time series plot. So again, it's a simple line plot, but you can call this line plot function multiple times, and you can specify the different colors for each plot, and you will get this kind of time series plot. Because others are the same as previous example, I think we don't need to address these. And let's move on to the final example file. In this example file, we'll show some simple regrading, the grid data method that was used in the zonal mean cross section. And you may want to save the grid data to new Xcdf file for your analysis, because sometimes you may want to play with structured grid instead of unstructured grid for some kind of analysis like zonal mean plot. So here we again load libraries and load one file as an example. And here we regrade the file, but in this case, we only regrade the file for the region of interest. And here we have 0.1 by 0.1 grid only for corners region. And the procedure is the same. So we construct the grid using this mesh grid function. And we have to get the latitude and longitude information from the model. And using this grid data function, you can do some simple regrading. And you can also choose different methods, such as a linear or near-least grid interpolation method. So we have two ozone concentrations from two different methods in this example. And for linear interpolation case, we multiplied it by 10 to the 9. So their units are different in this example. Then this is the part for writing the output to the Xcdf file. So you have to first specify the file name with writing option, and you can also change the format. So for example, some models don't like Xcdf 4, so you may want to change it to Xcdf 3. And then you have to first create the dimensions. In this example, because we don't have time dimension, we only loaded one data set. So we just created two dimensions, one for latitude, the other for longitude. And we have to set the variables with the dimension informations for latitude, longitudes, and two ozone mixing ratio calculated above. And because their units are different, you want to include this information in the nested files. You can simply assign attributes by using this dot and whatever name you want. In this example, units. And then you can set the different attributes for different variables. And then you have to assign the variables to this created variable for Xcdf file. Then make sure you close this Xcdf file so that you don't have any errors with this. So yeah, that's all we have. And we'll have some time for you. So you try your examples on Jupyter Hub or on your local PC, and we'll get any questions.